Good enough. Okay, perfect. All right. Well, hello everyone. Thank you all for being here. It's my pleasure to introduce Brian DeWolfe, who is visiting from Toronto Metropolitan University. We met at Complex Networks Winter Workshop. Chapon was there at Quebec City this year in December. It was a fantastic time. Brian works on processing data mining in network data, and so sort of problems that are very, and kind of dissecting methods in really interesting ways, problems that are kind of interesting to me. Really excited for your talk, and thanks for coming and being here.
Great. Thank you for organizing on such short notice, and everybody for coming out. Very nice to get to speak to people interested in the demo. So this is some work that I've kind of been thinking about over the last maybe year or so. There's two sub-projects here, and we're starting with the second one, just because I think the story is nicer that way. And this is very focused on techniques for community detection. I think there's some interesting avenues in this area. So football graph, fairly popular, one of the classic community detection graphs. And I hope you will agree that a partition is not maybe the right way to be thinking about this. You've got all these teams in the conferences that are very clearly communities. They've got lots of these internal edges, but then all of these black triangle nodes are independent teams. They are classified as one conference, but they don't really play each other. They just kind of play other randomly. So I'm going to call these outliers. They don't look like they're part of the group, but they're very weakly part of some group. But maybe we want to be able to say that into something else. We don't want to force them into kind of stronger groups. Okay, so the way we're going to do this is by borrowing from HDBSCAN. It's kind of under the hood. If you ignore the vector data, it's hierarchical single linkage clustering. See how you can apply this to graph data to get outliers for free. And then if you do this edge clustering lens, you also get some overlap for free. I'll try to breeze through those a little quickly to what gets to be, I think, the interesting part, which is the temporal hypergraph edge clustering. It's a big application of this. All right, so hierarchical single linkage clustering. There are kind of a couple standard ways to do community detections. One of them is these divisive algorithms. Everything is in one community at the start, and you're going to split it in some way instead of usually two subpieces. Sometimes you can do more. And then every time you split, we'll drop one level down. Dendrogram here. And then usually at some point to actually get the clusters, you have to choose where you're going to put this. Each of these lines that intersects your horizontal cut will be the clusters. The opposite, these are computationally tractable approaches. There's agglomerative, it tends to start in its own community and then merge communities according to some measure pulled out of somewhere. And at each step, we can walk up the dendrogram. So previous one was top down. This one is bottom up. This is walk trap. Louvain is doing something similar. And single linkage clustering is both something in the middle. Basically, if you set the distance between clusters as the minimum distance, you have some metric distance. And we say we're going to merge the clusters of the distance instead of the iteration. So as we walk up, the distance is increasing. Then there's a very nice kind of topological approach. You can do this bottom up or top down split once the distance passes some threshold. And the interpretation here is that we're taking connected components in some graph moves up our clusters. So in particular, if we have some distance on all of the edges of our graph, drop all of the edges that are farther apart than your cut level D, and then the clusters are just the connected components of it. So this is kind of, we can get right at the middle of the tree without going bottom up or top down. That makes this very nice top level approach. Right, so we have these dendrograms. We've seen 5 or 6 different clusters at the bottom here. If you're doing from agglomerate where each node starts as its own cluster and you have a big graph with say 1 million nodes, this dendrogram is really hard to work with. Can't visualize it. It's 1 million individual clusters feels like way too many. So we can condense it with a simplified version of, if we zoom out and kind of squint, what does it overall look like? So the first step, that's just kind of to follow the HDBSCAN notation. We want to switch from distance to 1 over distance. Doesn't change everything, but now we start at 0, increasing 1 over distance as we go down. And then basically we just go and we cut off any branch that has fewer than some minimum cluster size vertices in it. So we're cutting off the small clusters as we get towards the bottom of the tree. Also, we select minimum cluster size of 2. This branch is 2, so it's good, but this branch is 1, so we would cut it off. This branch is merge into 1, so just this one big thing here. That these stems off. And then the same on this side, we can cut this one off. This will become 1, and then this will be when they fall out into their own clusters, you would have to cut each minimum cluster size of 2. So there is this minimum cluster size parameter that's somehow related to resolution. Big clusters will be, maybe it's a bit more modularity resolution.
So there on the right, if the minimum cluster size is 2, we have to move up a level on the right hand side of the tree.
Yeah, so this bottom level here is
okay.
It's slightly shifted. There'll be some maybe nicer examples of condensed dendrograms later. So once we have this condensed dendrogram, if you're like very competent in data science, you can maybe learn something about what is the structure of your graph. But for lots of applications, you actually mean like, here are the list of communities. This is the list of clusters. So we're going to define some optimization problem on this tree to give us a set of these. Basically, the way we do this is equivalent to finding the maximum amount of area on this graph. Is a non-overlapping set of bars to maximize the area. We kind of give each point contribution score to the cluster based on how long it's in the cluster. So that's height. And then if it has lots of points on the condensed graph, it's drawn as a wide bar. So summing the length of time the points are in the cluster, how many points there are. So we're basically doing an area computation. Yeah, it's a tractable optimization problem to find this set of non-overlapping clusters out of the condensed dendrogram. So some positives about this method is we get outliers here. If the very first thing that happens is 1 point falls out of this cluster tree and that comes at the minimum cluster size greater than 1, that branch immediately gets cut. So we're not allowed to choose it as a cluster, so it's not in any cluster. So these are going to be the outliers, and we don't have to like do anything else to it. This optimization method of just non-overlapping clusters allows for different resolutions, or densities, or distances. So if it splits into 2 very high on the tree, and then the second one splits into 2 very low on the tree, we don't have to draw a single horizontal line through the tree. We can kind of select at these different levels. Finally, for me, an important part is that quite fast. Do n log n, where n is the number of vertices, so millions, no problem. Right. So that's the hierarchical single linkage. This is kind of what's sitting under HDBSCAN, and I'm going to be sitting under some of the proposed methods today. So the very best case scenario is basically we choose some very good edge weights so that our condensed dendrogram looks something like this. This is the football graph where we have these 10 very large bars. Persist for a long time, and they all merge at a similar-ish range, but maybe not exactly. It looks like you could maybe draw a horizontal bar to get all of these. That's not the case. But I've just kind of been pushing this into if you can choose a good edge weight, then the method works. So how do we choose a good edge weight? Yeah, the clusters that you get. All the -1s are those outliers. Almost perfect. Not quite rare. So I do have some ideas about what an edge weight might be. Literature review. This is actually a very popular first step. If you want to make a lead and do a little bit better, there are tons of different ways you can slightly weight your graph to kind of improve the performance. In the data science context, it matches some ground truth community better. So we tested a bunch of them. If something exists already and it works very well, then we'll just do that. Yeah, we tested on some synthetic networks that do have outliers. ECG seems to do fairly well, but maybe none of these are doing exceptionally well. And then if we test it on some real graphs, we can see all of them. There's at least one existing edge weighting option that will do a little bit better than the way, but it's not at all consistent which option that is. So you don't know which option to choose, and when you don't have that, you can't check if you chose a good option. But at the very least, it seems like this is reasonable. Similarity score. Right. So that was just community detection with outliers. We can now get some form of overlapping communities too by switching from vertex clustering to linkage clustering. So in this case, we cluster all of the edges. You can still have outlier edges. Previous section, I know if all of your edges are outlier edges, then you don't have a community. We only project these edge clusters on by including the node in the community if that's at least one edge. Probably set a threshold on this. I'm not sure how you should pick that, so we'll just do one. And so now instead of node similarities, we need edge similarities. Basically what this is you're choosing some weighting of the line graph. So you can build a line graph, which is take each edge in your original graph and associate it to a vertex in the line graph. And if two edges are adjacent to the original graph, the vertices will be connected. So edge similarities, you can store this as a weighted line graph. And then we have a weighted line graph, you can just run a hierarchical single linkage clustering on it. We'll see what we get. Once again, there are several existing options. So let's test them to see if they do well. This time on some synthetic graphs that do have overlapping communities. And performance tends to be much worse. Actually, overlapping communities is quite difficult. But maybe once again, if you just run them on the real graphs, you can do slightly better than if you had just run the RAM on the line graph. But there's not a single edge weighting score that works well. So choosing this, if you could write down a good similarity score, I think this method has promise. Actually writing down that good similarity score is still open. But on the topic of if you can write down a good similarity score, that's kind of up to you. This will be the how are you defining similarity? Maybe it's for the particular problem. Maybe this option. This was actually the first project that kicked this off. I was thinking about how do we do this temporal hypergraph clustering, and you'll see we can build a similarity score that does something we think we want, and then once you have a similarity score, just run them hierarchical single linkage clustering. Right. So maybe Network Science Institute, generalizing a graph to a hypergraph, we just let an edge have any number of vertices instead of all two. So we're going to track this as an incidence function because it copies an edge, temporal aspect here too. But this is a generalization of our graph. So the example of this is a collaboration paper. If 3 authors write 1 paper, that's very different from 3 papers with 2 authors each. So we're going to model this as a hypergraph where authors are nodes, papers are vertices, and then our incidence function is blocking half a paper to a set of authors. We scraped archive for about 6 years. We get about 1 million authors and 1 million edges. So not gargantuan, but fairly large. We can do a little bit of EDA on this hypergraph. The rate of papers is going up. But for later, importantly, it's not going up so extremely that the rate over here is completely different from the rate over here. If we had extended this to maybe my archive is reduced, then it's only getting a couple of papers, maybe a week. That would cause some problems with this method. But in this case, it's okay. We don't have to worry too much about the rate at which papers are being published overall. So the kind of motivation behind this project is, suppose that we're looking for persistent collaborations between groups of authors. If you want to be able to take out research labs, guess who might work with who, you could do some link prediction thing. But beyond just, oh, they wrote 1 paper together. Lots of people write papers with 1 or 2 other people. But if you consistently write several papers together over the course of some non-trivial amount of time, that's probably evidence of a meaningful connection. So the way we're going to do this is do paper edge clustering to find groups of papers that occur at similar but not identical times, and then over them and have similar authors. So this is where the specific project, we're just going to think up edge similarity measure that we can answer this problem. So we want similar set of authors. We can just take Jacquard index of the author sets. So importantly, if they're not overlapping, then this score will be 0, which means that you only have to look at adjacent hyperedges to get all of the non-zero structural similarity scores. Yeah, and if they're identical, it's 1, and then between it behaves reasonably. So we have some structural sense, but this is a temporal hypergraph. We also wanted them to be fairly close in time. So we can put some kernel on how far apart these edges are in time. And we want to keep, so if they're too far apart, we want to set it to 0 to make the line graph sparse. It's kind of easier to work with. We're just going to choose some maximum time and then do a kind of linear based on that. So different choices of our maximum difference in time to produce a non-zero similarity will give us just different kind of time resolutions, which we'll look into. And finally, we want to get one edge weight for the line graph, so we just want to combine these in some nice way that if either of them are zero, then the whole score is zero. And if both of them are maximally similar, we still want it to be maximally similar. So we'll just take the square root of the product. And yeah, so if they don't overlap at all, or they are far apart in time, the similarity will be zero, which we can tune to make the line graph extremely sparse, kind of as sparse as we need for the algorithm to run fast enough on the computer. Okay, so we have this archive data set, about 6 papers, and we test 2 temporal similarity graphs. So the first one, sigma is 360, that means 2 papers can be up to a year apart and still have non-zero temporal similarity. So as long as you guys are publishing at least 1 paper per year, 2 to get it kind of towards the middle of this kernel, then you can reliably have similar papers. And we can see that the cluster lifetime, so this earliest paper in the cluster versus the latest paper in the cluster, fairly well spread out. Most of them in the 2 to 3 year range, but some of them get all the way up to a full 6-year data set, where authors will be consistently publishing together for up to 6 years. However, if we really narrow the window down to 30 days, so this is you have to publish multiple papers in a single month to get any similarity between those papers. Basically, all of the cluster lifetimes are like 2 months long. Digging into it a little bit, most of it looks like 1 or 2 people have dumped all of the papers onto archive on the same day. So very different behavior in how long these clusters are. Maybe you want to look for instances where somebody published a whole ton of papers on one day. Then you can just set your window very narrow. Maybe you want to see these long, persistent collaborations, you can set it a little bit wider. So there's some flexibility here. So digging into these cluster structures. So this is the line graph. This is a cluster that was found on the line graph. Maybe it doesn't look like a modularity cluster that much. It's not that dense. But because single linkage relies on the kind of minimum edge weight on a connecting path, these are organized according to time, and you get this one very strong edge kind of to each next orbital space edges here. But there's one very strong path through this cluster, and this is why the single linkage clustering algorithm is nice for this kind of problem where we have to stretch a long ways of time. We don't have to consider the fact that the nodes at the end can never fall to the cluster. They can exist in these kinds of long path-like structures. So we have our clusters, right? Some set of papers. We can make some cool visualizations with them to kind of dig into it a little bit more. And this is more hypothetical about what do I think we could do with this data rather than actually having an end goal here of figuring something out. So each paper has a topic. So it was published on one of the archive topics. So a group of papers will have a group of topics. We can say that a cluster of papers is a distribution of topics. The map works on distributions, so we can map these topic distributions down to 2D and see what are the topics that each of the collaborations will publish on. So each of these points is a group of papers that we believe is some research group, maybe it's an institute, maybe it's just a very strong collaboration between some professors. And we can see that the topics separate reasonably. There are lots of groups of people that only work on astrophysics stuff together. And maybe an interesting thing here is you're looking for other groups, maybe you're a postdoc, what other groups are publishing work similar to what I'm doing. You would go find whatever cluster your papers happen to be in, go look at the nearby ones. Those are other groups of people, some topics maybe you want to go talk to them. So this structural similarity, we can replace it with something else. There's no need for it to only be the vertex. And a few years ago, there was a lot of interest in this simpliciality or encapsulation. Basically, one hyperedge sitting entirely inside of another hyperedge. So we can just write that as the similarity measure. So they can be similar if one is entirely inside the other, and they will have zero similarity. You can run this, you will get clusters. Basically, all of the clusters will, but this you have one edge of size 1, and all of the other papers that got published by that author nearby also get some similarities to that paper of size 1. But maybe there's reasons that you care about this in the more general case. You can drop the edges of size 1, size 2. It's going to help find like what is the core of the group and how long there's regularly contribute. Maybe that can help. But the point is that the structural similarity measure is flexible. So this is a conference paper. There are some other ideas in there. You can take a group of papers as a distribution of the number of times each author contributed to that cluster of papers. And you can do the same UMAP trick, and then if 2 points are very close together, but maybe they took a break in a year. If you take 2 years off, there will be no temporal similarity, so that has to be 2 different clusters. But if it's the same group of authors, then this would happen. Maybe you can find these non-persistent collaborations. We also tested their structural similarity measures looking at hyperedge sizes. So we can get basically we can pick out the very large physics experiments because they have lots of authors in common, and it's very rare to have 1,000 authors on the paper and not being these physics experiments. So I think this is still a work in progress. I think the idea of the temporal similarity is interesting, but there are some problems in this approach that we don't have the solutions for yet. So I said at the beginning that the rate of papers published was not extremely different over time. That would be important. You can you need to do some scaling on your time similarity if it was very sparse in one time and very dense in another time. But also doing this somehow local. The rate that papers are published in machine learning is extremely different than the rate in number theory. This approach right now, we only have one time kernel parameter option. So we maybe can't capture, or we can't tune it to fit well on machine learning timescale and also well on the number theory timescale at the same time. So some sort of locally aware time would be interesting. Yeah. You have some locally aware time kernel, maybe you can do some temporally aware random walks. And this will get you all of the right walk tools, no-to-vec, edge-to-vec. There's a hyper edge-to-vec talk that's in the works from PNL. I'm not associated with, but saw the talk and it's good. But I think that this temporally aware random walk would lead to some very interesting applications. And then finally, structural similarity measures that you can write down your own. So in the money laundering literature, there are these patterns that they think are associated with money laundering. So if you have some short cycles that don't have any intermediate edges, if you can find a way to encode that in a similarity score, then you can build a line graph, a hyper line graph, if you need to include multiple nodes in one similarity measure. And then if you can cluster that in some meaningful way, that will help with money laundering, where a lot of these suspicious patterns occur with similar nodes at a similar point in time. You want to flag that. All right, so the summary is that hierarchical single linkage was taken from HDBSCAN. It's very flexible as long as you're okay defining your own notion of what is similar. You can do edge clustering, which will allow for some overlap on the clusters. Hyper edge clustering is temporally aware. If you write down your own similarity measure, then we can use to apply hierarchical single linkage. But also writing down a good similarity measure is not trivial, and it's probably. So whatever specific problem you're working on, you might have to tweak it a little bit. So thank you for coming out. Most of this was published in these 2 conference papers, which are also available on archive. If you would like to look at all of the details and all of the plots, there's some time for questions.
I know a couple people have to run too, so first question, I guess this is really cool, awesome. Just like specifically, you said, okay, I found 1,600 communities here, 1,400 communities, depending on sort of time resolution kernel. What did the cluster size distribution actually look like? You showed one community that had 13 nodes in it, or 13 edges, if I remember. Like across all 1,600, are they small? Are they big? Are some of them massive? What?
If the kernel is narrow, most of them have very few number of papers in them.
Yeah.
If the kernel is large, most of them have kind of a medium number. I don't think it's exactly power law, but it's definitely not concentrated. Some of them have a lot of papers, some of them have very few, and a sharp boundary at the minimum number of papers to be considered a cluster.
Sure.
As for the number of authors in the cluster that contributed to this cluster, it varies wildly.
Oh
yeah, the physics ones, a single paper can contribute 1,000 authors.
Sure.
Whereas in math, the number theory world, a single paper here contributes 2 or 3.
Yeah, so like the collaboration patterns of the fields determines the sort of like authors per paper determines how many authors
are in a set of papers.
Yeah, set of papers. And then does that kind of trick the algorithm in some way? So if you define whatever distance score on, do they just like look different? Does the distance measures look different for different kinds of collaboration patterns, or?
So the probably yes, but I'm not convinced that that's a bug and not a feature.
Yeah.
In one of the experiments that I didn't show here, to get all of these very large physics experiments, basically we at the threshold that say the edges can be too dissimilar in size. So if one edge has size 500, it's only allowed to be similar with edges of size between 4 and 600 to kind of stop a 3-author paper from being at all similar to a 500-author paper. Semantically, it's very different things.
Right.
So you can tweak it in a lot of ways to kind of get these different patterns to show up in the line graph. So I think it depends on what exactly the problem you're trying to solve is. You can custom together something.
Yeah,
Especially on like this is all, yeah, thank you for sharing, because I like this is the types of questions that as a PhD student I was really interested in, and I wrote about them and sort of assumed that everyone else in the world, but and so it's good to see that there's development. For like bipartite graphs or graphs with like not clear sort of community structure, is there just like some, would it just be some fancy or edge group that sort of like a repellent edge rate in a way, or do you kind of see a way to adapt this to more generic notions of partition and just like dense subgraphs?
Yeah, so I think anytime you can write down some function of your belief that these small group of nodes or these two nodes belong in this same community, you can probably do this approach. There's some spectral things that I've read where it's you get communities that are internally sparse and dense to the rest of the graph. I don't think something like that would work with this approach because you kind of need to build it off of a similarity measure. Complement to the similarity measure removed, but you need to be able to say, I have some belief that this small group of nodes belong in the same group, whatever that is.
Yeah. So I'm just running into class, but
there's a question. Maybe I'll ask one more. I mean, you're starting to allude to this a little bit, but it seems pretty critical to choose this distance function in some kind of smart way. And you alluded to a few cases where you can actually use the sort of problem domain, like you know what a paper size 300, paper size 500, like you kind of have a notion of what similarity is there. Do you think that there's some like progress that can be made on the sort of hyperparameter choices there? What actually similarity choices can be made?
Yeah, I think there's definitely room for a generic similar option, which the end of the first section with our just clustering a graph. You say you want dense subgraphs. I think there's hope for like a generic option that works fairly well. It's not going to work perfectly in every single case, but it probably will work better, or at least more consistently than the existing options. But I do think that a part of the power that is held by similarity is for it no additional information that you can encode that into this function. Instead of using these that don't know about your specific problem.
Yeah. That makes sense. Well, cool. Thanks so much for sharing. Yeah, thanks for having one more time.